Good evening, sir.
Yes, good evening. We will start soon. Okay, so let's start today's session. First, we'll solve a problem.
Hello everyone, in this video I shall discuss the solution of question number 54 of GATE Physics 2020. This is a numerical answer type question. For a gas of non-interacting particle, the probability that a particle has a speed v in the interval v to v plus dv is given by f v dv equal to 4 pi v square dv into m by 2 pi kt whole to the power 3 by 2 into e to the power minus mv square by 2 kbt. If E is the energy of a particle, then we need to find out the value of E by kBt at which the maximum in the corresponding energy distribution occurs. Let's solve this question. We have f v dv equal to f tilde e dE, where f tilde e is the probability that a particle has energy between E and E plus dE. Here E equal to half mv square. So dE is equal to mv dV. So F tilde E is equal to fv by mv. Now in this problem we have fv equal to m by 2 pi kt whole to the power 3 by 2 into 4 pi v square into e to the power minus mv square by 2 kVt. This can be also written as root 2 by root pi into root m by kVt whole to the power 3 by 2 into v into e to the power minus mv square by 2 kVt. Now we need to replace v by root 2e by m. So if tilde e is equal to root 2 into root m by root pi into kVt whole to the power 3 by 2 into 2e by m whole to the power half into e to the power minus e by kVt. After some simplification, this can be written as 2 by root pi into e to the power half by kVt whole to the power 3 by 2 into e to the power minus e by kVt. Now for the maximum of f tilde e, we have df de equal to 0. So d capital E of capital E to the power half into e to the power minus capital E by kVt equal to 0. This means half into E0 to the power minus half into e to the power minus E0 by kVt minus E0 to the power half by kVt into e to the power minus E0 by kVt equal to 0. From this equation we get that E0 is equal to kVt by 2. So we have E0 by kVt equal to half, which is equal to 0.5. So the correct answer of this question is 0.5. So the correct answer is 0.5.
Okay. So is there any question? Hello?
The speed of the video is too
Okay.
fast.
Right.
Yes, sir.
Okay. I will explain to you again.
Okay, sir.
So am I audible?
Yes, sir.
Okay. So you know about this thing, this Maxwell's velocity distribution. If v dv equal to this is already given in this question. Okay, now you have to find out the same thing, I mean the distribution in terms of energy. This is the distribution in terms of velocity, right? Speed or velocity. So now you have to find out the distribution in terms of energy. Okay, and the particles are non-interacting. So what is the total probability, I mean this thing, sorry, this is equal to 1 because sum of all the probabilities is 1. This is clear? Hello?
Sir.
Okay, now the same thing holds for energy, right? This is equal to 1. So these two integrals are equal, so we can write it like this: f v dv equal to f tilde e into dE. Now you know that for non-interacting particles, ideal gas particles, the energy E is equal to half m v square, where v is the speed and m is the mass of the particle. Okay. Now put this v dv here, this expression here. Okay, and let's find out this f tilde e. So f tilde e is given by fv dv by de, right? So what is dv by de? This is equal to 1 by mv. So this f tilde is equal to fv by mv. This is clear?
Yes, sir.
Okay. Now let's put the expression of fv, the expression given in the question here. Okay, so I have just put the expression here, and now we after some simplification we get f tilde e as this expression. Okay, now you have to write this thing in terms of energy, right? So what is v in terms of energy? So we have E equal to half m v square. So v is equal to root over of 2e by m. Okay, now replace v equal to this thing root over 2e by m in this expression. Okay,
Sir.
so if you put this, and after if you do some simplification, then so you get this expression. Now you have to find out its maximum. So how to find out its maximum? So for the maximum of f tilde e is given by del f prime del e, del f tilde del e at e equal to some e0, where e0 is the value of energy where the maxima occurs. Okay, and this is equal to 0. The simple thing, you have to find out the maximum of this by doing the differentiation with respect to energy and set it to 0. Okay, now it's very simple thing now. So just find out the differentiation of this thing with respect to energy E. Okay, so if you do that, and after if you do some simplification, then you get this thing E0 is equal to kVt by 2. Okay, so E0 by kVt is equal to half or 0.5. So the maximum of this energy distribution occurs at E0 equal to kVt by 2 or 0.5 into kVt. So this question correct answer is 0.5. Okay, any question?
No, sir.
Okay. So this question is clear.
Yes, sir.
Okay. Now let's proceed with another question.
Hello, 2i plus alpha theta square by 2. Hello everyone. In this video, I shall discuss the solution of question number 15 of GATE Physics 2020. A small disk is suspended by a fiber such that it is free to rotate about the fiber axis. For small angular deflections, the Hamiltonian for the disk is given by h equal to p theta square by 2i plus half alpha theta square. where I is the moment of inertia and alpha is the restoring torque per unit deflection. The disk is subjected to angular deflections theta due to thermal collisions from the surrounding gas at temperature T, and P theta is the momentum conjugate to theta. We need to find out the average and the root mean square angular deflection theta average and theta RMS. Let's solve this question. In this problem, we have the Hamiltonian H equal to P theta square by 2I plus half alpha theta square. Here, theta average is defined as integral dp theta integral d theta into theta into e to the power minus beta h by integral dp theta integral d theta into e to the power minus beta h. Here we replace h by p theta square by 2I plus half alpha theta square. The integral of p theta in the numerator and the denominator cancel out. So we have theta average equal to integral d theta into theta into e to the power minus beta alpha theta square by 2 by integral d theta into e to the power minus beta alpha theta square by 2, and the limits of this integration are minus theta naught and plus theta naught. We obtain that theta average is equal to 0 because the integral d theta into e to the power minus beta alpha theta square by 2 is equal to 0 because the limits of the integration are minus theta naught and plus theta naught. This integral can also be written as integral d theta into e to the power minus beta alpha theta square by 2, where the lower limit is minus theta naught and the upper limit of this integration is 0 plus integral d theta into e to the power minus beta alpha theta square by 2 with the lower limit of this integration 0 and the upper limit of this integration is theta naught. Now the first integral can also be written as d theta prime into theta prime into e to the power minus beta alpha theta prime square by 2 with the lower limit being theta naught and the upper limit of this integration being 0. Here we assume that theta prime is equal to minus theta, and the first integral can also be written as minus d theta prime into theta prime into e to the power minus beta alpha theta prime square by 2 with the lower limit of this integration being 0 and the upper limit being theta naught. Thus we see that the first integral and the second integral cancel out. So we obtain that theta average is equal to 0. Now the theta RMS square is equal to integral dp theta into d theta into theta square into e to the power minus beta h by integral dp theta into integral d theta into e to the power minus beta h. Here also we replace h by p theta square by 2I plus alpha theta square by 2. The integral in p theta in the numerator and the denominator cancel out. Thus we have only the integral over theta in the numerator and the denominator. So theta RMS square is equal to integral d theta into theta square into e to the power minus beta alpha theta square by 2 by integral d theta into e to the power minus beta alpha theta square by 2. Let y equal to integral d theta into e to the power minus beta alpha theta square by 2. If we differentiate the both sides of this equation with respect to alpha, then we obtain that the numerator of the expression of theta ms square is equal to minus 2 by beta into del alpha of y. So theta rms square can be written as minus 2 by beta into del alpha of log y. Now y is equal to integral d theta into e to the power minus beta alpha theta square by 2. Let's assume that beta alpha theta square by 2 is equal to v square, or theta is equal to root over 2 by beta alpha into v. Here we replace theta by 2 by beta alpha whole to the power half into v. So you obtain that y is equal to 2 by beta alpha whole to the power half into c, where c is a constant and independent of alpha and beta. So log y is equal to minus half log beta alpha by 2 plus log c. Now if we differentiate it with respect to alpha, then we obtain that del alpha of log y is equal to minus half into 2 by beta alpha into beta by 2, which can be simplified to minus 1 by 2 alpha. So minus 2 by beta into del alpha of log y is equal to 1 by beta alpha, which is equal to kbt by alpha. Now theta ms square is equal to minus 2 by beta into del alpha of log y. So we obtain that theta ms is equal to kbt by alpha whole to the power half. So we have theta average equal to 0 and theta ms equal to kbt by alpha whole to the power half. So in this question, option B is correct.
Should I explain again or
No,
everything?
sir.
So everything is clear, right? Everyone? Or any question?
No, sir. No question.
Okay. So let's proceed with the third question of this session.
Hello everyone. In this video, I shall discuss the solution of question number 49 of GATE Physics 2019. This is a numerical answer type question. In a thermally insulated container, 0.01 kg of ice at 273 Kelvin is mixed with 0.1 kg of water at 300 Kelvin. Neglecting the specific heat of the container, we need to find out the change in the entropy of the system in joule per Kelvin on attaining thermal equilibrium. Let's solve this question. In this question, we have heat released by water at 300 Kelvin equal to heat absorbed by ice at 273 Kelvin. Now let's find out the latent heat absorbed by ice. This is equal to m1 into L, where m1 is the mass of ice, which is equal to 0.01 kg, and L is equal to 335 kilojoule per kg. So we found that the latent heat absorbed by the ice is equal to 3.35 kilojoule. Now let's consider that the final temperature on attaining the equilibrium is equal to Tf. The temperature T1 is equal to 273 Kelvin and the temperature T2 is equal to 300 Kelvin. We have heat absorbed by ice at 273 Kelvin equal to heat released by water at 300 Kelvin. This equation can also be written as the latent heat absorbed by ice plus heat absorbed by water at 273 Kelvin equal to heat released by water at 300 Kelvin. The latent heat absorbed by ice is equal to 3.35 kilojoule as we have derived before, and the heat absorbed by water at 273 Kelvin equal to m1 into s into Tf minus T1, and the heat released by water at 300 Kelvin is equal to m2 into s into T2 minus Tf. Here m1 is equal to 0.01 kg, m2 is equal to 0.1 kg, T1 is equal to 273 Kelvin, T2 is equal to 300 Kelvin, and the specific heat S is equal to 4.2 kilojoule per kg into Kelvin. Putting these values and after doing some simplification, we finally obtain that the final temperature is equal to 290.29 Kelvin. Now let's find out the change of entropy in melting of ice. This is equal to delta S1, which is equal to delta Q1 by T1. Here delta Q1 is equal to M1 into L. Putting the values of M1, L and T1, we obtain that the change of entropy in melting is equal to 0.012271 kilojoule per Kelvin. This can also be written as 12.271 joule per Kelvin. When the temperature of water is changed from T1 equal to 273 Kelvin to Tf equal to 290.29 Kelvin, then the change of entropy delta S2 is equal to the integral dq by T. Here dq can be written as m1s into dt. Here the limits of the temperature T are T1 and Tf. So you obtain the change of entropy delta S2 is equal to m1s into log Tf by T1. Putting the values of m1, s, Tf and T1 and after doing some simplification, we obtain that delta S2 is equal to 0.002579 kilojoule per Kelvin. This can also be written as 2.579 joule per Kelvin. When the temperature of water is changed from T2 equal to 300 Kelvin to Tf equal to 290.29 Kelvin, then the change of entropy delta S3 is equal to m2s log Tf by T2. Putting the values of m2, s, Tf and T2 and after doing some simplification, we obtain that delta S3 is equal to minus 0.013819 kilojoule per Kelvin. This can also be written as minus 13.819 joule per Kelvin. So the total change of entropy delta S is equal to delta S1 plus delta S2 plus delta S3. Here delta S1 is equal to 12.271 joule per Kelvin, delta S2 is equal to 2.579 joule per Kelvin and delta S3 is equal to minus 13.819 joule per Kelvin. So the total change of entropy is equal to 1.031 joule per Kelvin. but in this question we need to write the correct answer up to 2 decimal places. So the correct answer is 1.03 joule per Kelvin. So in this question the correct answer is 1.03.
Hello, am I audible?
Yes, sir.
Okay. So this was the question, right?
Yes, sir.
Okay. So we have 0.01 kg of ice at temperature 273 Kelvin and 0.1 kg of water at 300 Kelvin. Okay, and they are mixed. Okay. Now we have to find out the change of entropy of the total system when the equilibrium is reached. Okay. Now we know that at equilibrium the heat released is equal to heat absorbed. So the ice at temperature 273 Kelvin will absorb heat, right? And the water at 300 Kelvin will release the heat. So these two should be equal. Now you know that ice to water phase transition occurs at 0 degree Celsius or 273 Kelvin, right? So the ice will absorb some amount of latent heat for this phase transition, ice to water phase transition, or this is called the latent heat of melting of ice. Okay, and this is equal to m1 into L, where m1 is the mass of ice and latent L, capital L, is the latent heat per unit mass. Okay, this is given already. So just put these values and you get this thing. The latent heat absorbed by ice at temperature 273 Kelvin equal to this thing. Now we have 0.01 kg of water at 273 Kelvin and 0.1 kg of water at 300 Kelvin, because the ice has already been melted. Okay, and the temperature of the water of mass 0.01 kg is now 273 Kelvin. So how to find out the final temperature? Again, let's put the quantities in this expression. Okay, so this is the expression. Now what is the heat absorbed by ice at 273 Kelvin? It is equal to the latent heat absorbed by ice and plus the heat absorbed by water at 273 Kelvin, and this is equal to the heat released by water at 300 Kelvin. This is clear?
Yes, sir.
Okay. Now this latent heat you have already calculated. Just put this value, and what is the heat absorbed by water at 273 Kelvin? This is equal to m1 into s into Tf minus T1, where Tf is the final temperature and S is the specific heat of water, and m1 is the mass of water, which is equal to, I think, 0.01 kg, and T1 is equal to 273 Kelvin. Okay, and this is equal to heat released by water at 300 Kelvin. Now the mass of water at 300 Kelvin is equal to m2, which is equal to 0.1, I think, kg. Okay, and similarly S is the specific heat of water and the final temperature is Tf, and T2 is this thing, 300 Kelvin. Okay, this is written here, these things are written here. Okay, just put these values and simplify, and then we will get this value of TF, the final temperature, which is equal to 290.29 Kelvin. Okay, now let's find out the entropies. So there are three processes. One is the melting of ice at 273 Kelvin. The another process is absorption of heat by water at 273 Kelvin, and the last process, the third process is the heat released by release of heat by water at 300 Kelvin. Okay, now let's find out the entropies one by one. So this is simple. Change of entropy of the melting of ice delta S1 is equal to del Q by T1. Okay, and you know that during the melting of ice the temperature remains constant, and this temperature T1 is equal to 273 Kelvin. And what is delta Q1? This we have calculated before. This is equal to m1 into L, where L is the latent heat per unit mass and m1 is the mass of ice. Okay, now put the values here. m1 is equal to 0.01 kg, L is this thing 335 kilojoule per kg, and the temperature T1, which remains constant during the melting of ice, is equal to 273 Kelvin. And simplify it. Okay, and write all the entropies in terms of this joule per Kelvin, because in the question you need to find out the total change of entropy in the units of this joule per Kelvin. So just convert the kilojoule to joule. Okay, and the Kelvin remains Kelvin. Okay, so you just need to multiply with 1000 for going to joule from kilojoule, right? And if the temperature of water at 273 Kelvin is changed to the final temperature, which is equal to TF equal to this thing 290.29 Kelvin, then the change of entropy delta S2 is equal to integral del Q by T. Now this del Q is equal to m1 into S into dt, and if you integrate it over the temperature range, then you will get delta S2 is equal to m1 into S into log TF by Ti, and this m1 is equal to again 0.01 kg, and this age S is given to you. This is equal to 4.2. Okay, and TF is equal to 290.29, and Ti, the initial temperature, is equal to 273 Kelvin. So just simplify it and write it in terms of joule per Kelvin. Okay, again. Now this is the third process. Here water from 300 Kelvin is brought to 290.29 Kelvin, or the temperature, final temperature TF. Now what will be the change of entropy? This is again you use the same formula, m2 into S into log TF by T2, where m2 is the mass of water which was initially at 300 Kelvin. Okay, and TF is this thing, and T2 is 300 Kelvin. Now we can put the values and simplify it, then you will get some negative quantity. This is expected, right? Because heat is released by the water at 300 Kelvin, so entropy will decrease for this water at 300 Kelvin. Okay, so again write it in terms of in the units of joule per Kelvin, and so the total change of entropy is equal to delta S1 plus delta S2 plus delta S3. So the first two terms are positive and the third term is negative. Just put the values as it is, and calculate, then it turns out to be 1.031 joule per Kelvin. Now in this question you need to write this answer up to 2 decimal places, so the answer will be 1.03 joule per Kelvin. So this is equal to 1.03 joule per Kelvin. Okay, so this thing is clear.
Yes, sir.
So I'll assume that there is no question. Then let's solve another problem.
Hello everyone. In this video, I shall discuss the solution of question number 10 of GATE Physics 2016. This is a multiple choice question. For a system at constant temperature and volume, we need to find out the correct statement at equilibrium. Option A, the Helmholtz free energy attains a local minimum. Option B, the Helmholtz free energy attains a local maximum. Option C, the Gibbs free energy attains a local minimum. Option D, the Gibbs free energy attains a local maximum. Let's solve this question. Helmholtz free energy F is given by E minus Ts, where E is the internal energy, T is the temperature, and S is the entropy. So the change of Helmholtz free energy dF is equal to dE minus TdS minus SDT. From the laws of thermodynamics, this dE can be written as TdS minus PdV. So dF is equal to minus PdV minus SDT. At constant temperature, dt is equal to 0. At constant volume, dV is equal to 0. So at constant temperature and constant volume, dF is equal to 0. So at constant temperature and at constant volume, the Helmholtz free energy F is extremum. Now the system always tries to minimize its internal energy. So also the system tries to maximize its entropy. Due to the maximization of the entropy and the minimization of the internal energy, the Helmholtz free energy F becomes minimum at equilibrium. This implies that the Helmholtz free energy attains local minimum at equilibrium. So in this question, option A is correct.
Is there any question? Hello?
No, sir.
So it has been discussed before, right? So just same problem again. Now we have time, so we'll have some discussion on this Maxwell's velocity distribution. So anyone knows about this derivation of this Maxwell's velocity distribution, or the distribution in terms of v? So I am just writing a simple way to do that. Okay, please mute yourself if you have no question. Please mute yourself if you have no question. Okay, thank you. So this thing you need to calculate. If v, let's say f of v0, okay, you have to find out the distribution at some particular v, the value of speed equal to v0. So how to do that? This is given by the expectation value of this thing. Okay, so you all know about the delta function, right? Dirac delta function.
Yes, sir.
Okay, now what is this expectation value? This is equal to z1, which is the single particle canonical partition function, which is in the denominator of this expression, and in the numerator we have this thing. Here d is the spatial dimension, right? So this thing is equal to this. Sorry, what happened? Oh. So this is clear, right? This is just the definition of some average value or expectation value. Clear?
Yes, sir.
Oh, I think there should be this factor 1 by h to the power d, where h is the Planck's constant, right? Now here the particles are non-interacting and they have no potential, so h is given by p square by 2m, right? And this z1 is equal to this thing, into e to the power minus beta h. Here I am writing h equal to this p square by 2m. This thing is clear? I hope it is clear. So there is nothing. Just
We take potential energy 0.
yes. You know that the ideal gas particles do not interact with each other and they have this Hamiltonian, right? H equal to p square by 2m. So you see this integral over this q, the generalized coordinate in the numerator and the denominator are same, and this factor is also same, h to the power d. So let's cancel it and simplify it. Okay, nothing else. Now this p is equal to m into v, mass times speed. This is the momentum, p is the momentum. Okay, now let's replace them. So we have so I am writing p equal to mv, so the energy will be half mv square, and there is 1 by kbt factor, so this is equal to this. Now this thing has been simplified, right? This m to the power d also cancel out in denominator and numerator. So what is this thing, d of v? This is the volume element in d dimension. So I think you all know this is equal to this thing. Okay, here this omega d is the solid angle in d dimension. And the solid angle is independent of v. Okay, so you can just cancel them from the denominator and numerator. Right? So this is now very simplified. Now let's first calculate the integral in the numerator. So we I think all of you know about the property of Dirac delta function.
Sir.
So what will be the value? This will be equal to v0 to the power d minus 1 into e to the power minus mv0 square. Right. Okay, just I have used the property of Dirac delta function. So if the value of v is inside this limit, then you'll get the value of this integral at that point, right? And if it's not there, then you'll get 0. So here we have v equal to, at v equal to v, this integral gets modified to v0 to the power d minus 1 into e to the power minus mv0 square by 2 kbt. Now let's calculate the integral in the denominator. So how to do that?
Gamma function.
Right. So we'll assume that mv square by 2 kbt equal to x, and let's say y. Okay, you can take anything there, that is not important. So what is v here? V is equal to this. So dv is equal to this thing. Now what was the integral, the denominator? It was, I think, this. Now replace it by v here. So you replace dv by this thing, and v by this thing. Okay, fine. Now let's just simplify this. So the integral of this 0 to infinity dy into e to the power y e to the power minus y into y to the power y to the power dy2 minus 1 is equal to gamma
divide 2.
dy2, right? This is the gamma function. So what we have obtained? We have obtained this f of v0 is equal to, what are the things here? Okay. So this is equal to this thing, right?
Yes, sir.
Okay. Now let's put d equal to 3. Let's see what happens. D equal to 3. Now here is gamma d by 3. Now what is the value of gamma d by 3? This is equal
Half root
to,
pi.
right, half of gamma of half, and gamma of half is equal to root pi. So this is equal to this. Now let's write it in proper way. I mean this 4 pi into v0 square into m by 2 kbt into pi into whole to the power 3 by 2 into e to the power minus m v0 square by 2 kbt. So this was the expression for if at v equal to v naught, right? It is matching with the expression we had in the question. Yes or no?
Yes, sir.
Okay.
Yeah.
So we are getting the correct thing, right? So in this way we have we can get the Maxwell's velocity distribution for any arbitrary spatial dimension d, right? Just put the value of d here. Okay, that's all. And from this you can also calculate these things. Probably you know this is already normalized. This if v dv is 1, integral of this thing is 1. This you can check for any arbitrary d dimension from this expression. Okay? And what is v average? V average is equal to this, right? Now the denominator is equal to 1, so you can just calculate this thing, that's all, if it is normalized properly. And Vrms square is equal to this thing, right? This is VRMS square, and again
square root over.
no, this is VRMS square, right? So if you calculate VRMS, then it will be right, this thing. Clear? Hello?
Yes, sir.
Okay. Now if you need to calculate the value of the speed where the probability of this distribution is maximum, then you need to do this thing. At v equal to some v star. Let's just calculate the value. Okay, so this can be a good homework for any arbitrary d dimension. Please do that if you have time to do that. Okay, clear?
Yes, sir.
Any question?
No, sir.
If not, then we'll stop today and we'll have our discussion on this statistical mechanics and thermodynamics on the next week from I think it's 1st October, right? From 6 p.m. Okay, and
Yes, sir.
the week after that, I mean from 8th October, we'll continue our discussion on classical mechanics, Lagrangian dynamics, Hamiltonian dynamics, Poisson bracket, canonical transformation, action angle variable, and things like that. Okay, so let's stop here. Thanks everyone for joining today.
Sir, can you share PDF?
Okay, is there any
I will share. I'll
option
give
sorry,
email ID.
is there any option to share it in chat in Google Meet?
Yes, sir.
No, I have not found it. Okay,
Sir, I will give you my email.
okay, so actually I want to send it to everyone, so don't send me email ID one by one. That will be a huge work for me, but I will try to send all the PDFs through this Google Meet chat or attachment. I think there is option. I have to check just. Okay, if I have time to check that, then I will do that within this week. Okay.
Okay.
Okay. So let's stop to the here.
Okay. Thank you, sir.
Thank you.
Good night.